Let's take a look now at continuous distribution, the normal distribution. We'll be using a new package that has a lot of statistical and probability functions in them. So this package is called SciPy, or SciPy if you're into that, stats, SciPy.stats. And we're going to be using various functions that describe the probability density and cumulative distribution functions within this package. So here I've got a basic plot of the standard normal distribution, and I'll just walk through what I've done here and what packages I'm using. Here's a little bit of a new syntax from you. So SciPy is a package in and of itself, and then this is basically a sub-package, stats. So from SciPy Stats, from that package within a package, so SciPy.stats, that delineates the kind of sub-package, import norm. And so norm is basically a suite of functions for the normal distribution. So we're going to then refer to norm and then the functions within norm. We'll use NumPy and then matplotlib. So I'm just bringing those back here in case you're starting from here. So first off, we need to plot this PDF. We need an array of X values, a 1D array. So we'll use the NumPy linspace function for that. And then we tell it where to start, when to stop, and how many values we want in that. So that's just going to give us essentially a vector or a 1D array. Now we feed that vector or array into the PDF function. So norm.pdf, that's the normal PDF function. That's going to give us our Y values or our density values. So we feed that X array into there, and then we'll call that Y PDF1. So now we're just going to use the matplotlib imported as PLT plot function. We're going to give it an X and a Y, and we're going to say call it red. Now the one thing I did here is I'm adding a vertical line, so that's called AXV line, and I say put that at 0. Here's the line style, here's the color, and you can play around with line styles and colors if you just search this function right here. I give it a title, an X label, a Y label, and then I say, okay, plot it between 0 and 0.5. That's something you might need to play around with. Finally, plot.show shows the plot. So there we go. And I just noted in the title that the mu is 0 and the sigma is 1. So this is our standard normal distribution. And I said that we've got z on the x-axis. I plotted it between -3 and 3. Of course, it goes out to -infinity and infinity, but the values get pretty small for probability density beyond that. Now we can start to shift and add a different spread to the normal PDF. So I'm going to use a different line here because I'm shifting it. I'm going to start at -10, stop at 7. I still want 100 values. So I create a new X2 array for the X values. I'm going to set the mean to -3, the standard deviation to 2.5. And then I'm going to create a new PDF or density values. So I'm going to call that Y PDF2. Using the same norm PDF, I feed in the X values. Now I'm going to add these parameters. So the generic word for basically a central tendency or expected value is location. And that's going to be used across a range of different PDFs, different types of PDFs. So the mean happens to be the location for the normal distribution, and then scale refers to the spread. So we're going to put in the standard deviation for scale. So location and scale are going to be the two parameters for normal PDF. Now, as before, I'll plot that. And you can see that now our mean was -3. And so I put that vertical line at -3 right here. And our standard deviation's going to be greater than 1. So the default value, if I don't specify in norm PDF, is going to be location 0, scale 1, or mean 0, standard deviation 1. So that's the default, is the standard normal distribution. But now that I've specified that, it's a little bit different. And you can see that it's lower, it's a little more spread out. And what I'm asking you all to do is describe that visually, compare the two, and plot them together on the same plot. So all you're going to do is bring those two sets of x and y values and just run the plot function twice. You might need to adjust the x limits. So pay attention to that. You might need to adjust the y limits, and then make sure to label these. So using the label argument and within the plot function. So give them labels. So standard normal distribution with mean -3 sigma 2.5, and then plot the legend. So we've plotted legends before in lab 1, and you can go back and look how to do that. Now we'll look at the standard normal cumulative distribution function. We'll use the same x vector from before, and now we're going to create a y CDF using the normal CDF function. So the normal CDF function is just going to give us that cumulative distribution from 0 to 1, and then we can plot that. Of course, I can change the scale and location in here if I wanted to. So if I just run this, I get my normal distribution. I can say scale equals 0, or sorry, location equals 0, scale equals 1, and it's going to give me the same thing. I can do location equals -3 and scale equals 2.5, and it's going to give me a different distribution function. I'd have to change the x-axis here if I wanted to plot the whole distribution. So right now it's not showing the whole distribution. So I'm going to just update that so that we get that same S-curve as before. Okay, so that's how we can plot that. And then here's just a way to plot two things side by side. We can use the subplot function, and basically I'm just saying how many rows, how many columns, and then which plot is this. So 1 row, 2 columns, this is the first plot. So that's 1, 2, 1, and then I just do all the plot functions as I would before. And this is going to be 1, 2, 2, and that plots it in this second position. Here's some other functions that I can use to kind of create some space in between it, and then plot them. There's a lot of other ways to do this. I just want to show you side-by-side plots. Now we'll look at using the normal functions within SciPy Stats to create a sample from that normal distribution, and we'll compare it to the theoretical. I'm going to be using the function norm.rvs. So RVS is random variables sample. And here I'm just giving it the size. So I want 1,000 samples based on the standard normal distribution. So that's our first sample. We'll call it R1, random 1. Then we can, of course, change the mean and standard deviation and take a different sample. So here I'm going to say, okay, random sample 2, norm RVS, here's the location, here's the scale based on the mean and standard deviation, and then here's the sample size. I want 1,000 as well. Now I'll plot histograms, and then I will plot those smooth curves over it just to show you what that looks like. So I'll define the bin edges, or the kind of bin intervals. I'm going to go between 10 and 8 at 0.5 for my interval. And then I'll plot the two histograms on top of each other. So hist plot.hist or plt.hist. I specify the bin edges, and then I want to plot density. That way the histograms and then the the PDFs will plot over each other. So density is going to be on the y-axis. I'll make them transparent using the alpha argument. And then here's my colors. Also, here's my label so that I can plot the legend and it'll label appropriately. So I'm just going to run that histogram function twice, and then I'm going to add lines based on the two probability distribution functions that I've already created. So here's the continuous line, here's my histogram, and you can see how the samples reflect the continuous distribution, but of course not perfectly, it's just a sample. Okay, so on your own, I've got this application. So it's a two-part problem here. The first is we're going to basically redo what we just did above, but with a different type of distribution. So we're going to say we're looking at a residential solar panel that on average produces 1.5 kilowatt hours in a day. So we're just going to probably say this is averaged over a year or something like that. And it's got a standard deviation of 0.4 kilowatt hours. So X follows a normal distribution of kilowatt hours with a mean of 1.5 and a standard deviation of 0.4. So what we're going to do here is on your own, create a sample of 100 values of daily kilowatt hours from this distribution. Call that sample KWH. And then what I want you to do for this first question is calculate the mean and standard deviation of this random sample that you just collected. So you've input the true quote unquote mean and standard deviation. You take a sample of 100, calculate the mean and standard deviation, and then compare. And then I want you to answer what is the sample statistic and what is the population parameter and how do they compare? How close are they? Now, please plot a histogram of your sample with 10 bins and then plot the probability density curve over that sample. So just following the same thing here, but here we'll just have one histogram and one curve. All right. So that covers these first three questions. Now, what I want you to do is transform that random sample of kilowatt hours into a z-score, where z is equal to x minus mu divided by sigma, and then replot the histogram based on the z-scores using density for the y-axis, and then plot the standard normal distribution over that. Comment on how this compares to what you did in the previous two exercises. So up here, where you just did the sample and then the PDF based on the mean and standard deviation. Finally, plot the empirical CDF of your kilowatt hours, your untransformed kilowatt hours. And to do that, you'll sort and then calculate the cumulative sum of that, dividing by the total. So if you go all the way up to our discrete example, we were using basically the same steps that we did from that first discrete cumulative CDF function. So you'll have a step plot basically, and then you want to plot that cumulative CDF from your data, from your sample, along with the continuous normal CDF using this normal CDF function. So you have two line plots on top of each other. Okay, so that's us looking at just kind of the distribution, histograms, and smooth curves based on the normal PDF and CDF. Now here's a little calculations for you for this last problem. So we are going to design a solar array panel, or sorry, an array of panels to provide power for a certain facility. The facility needs 20 kilowatt hours at least over the course of the day. And of course, it's going to be tied into the grid for nighttime and cloudy days. We want to size the array. Basically, how many panels do we need in this array to meet this average daily demand with a certain probability? So I've got a few questions for you. I want you to show your calculations within code cells with comments to say what you're doing, and then respond to each question within markdown cells. So typing out your response after you do the calculation. So the first question is, how many panels, integer, right? How many whole panels does this array need if we want to meet or exceed this average daily power requirement 95% of the time? So basically, we want to have a cumulative probability of 95% that we have 20 kilowatt hours or greater. So what's the mean of this new distribution? And assuming that the mean of an individual panel is already given, I gave you that 1.5 kilowatt hours. Standard deviation of an individual panel is 0.4. But then the mean of the whole array is just going to be additive. So if I want to find the distribution of power output of my array, I'm just going to sum up the means based on the number of panels that I have. So it'll have a new mean, but the standard deviation will stay the same. So the standard deviation of the array, no matter how many panels you have, will have the standard deviation of the individual panel. Okay, so essentially you're going to come up with, you're going to do this calculation, and you're going to basically find what's this new mean, so that 95% of the time, the power output's greater than 20 kilowatt hours. Now I want you to plot the PDF and CDF of this new distribution for your array based on the mean of the array and the standard deviation of the array. And then plot critical values, either vertical and or horizontal, based on this threshold, right? So show the cumulative, on the cumulative distribution, kind of show where we'll have that 95 percentile value and show that same thing on the PDF. So we'll basically have a line at the PDF, vertical line showing where we have cumulative 95% probability, and you'll show that same thing on the CDF associated with a value on the x-axis. All right, so that's all we're doing for this lab. Hit me up if you have any questions or get stuck.